Ready to go? How's it going? Hope you had a good weekend. It was a long weekend, so everyone should have fun, right? Uh, okay, today finally, like after so many weeks of talking about what's inside the process, how it gets linked and everything, we'll take a look at the first lines of the operating system code, which is kind of exciting, right? So today we're gonna learn how we're gonna boot into main on real hardware. And I will show probably next time that it actually works. And the reason you have to pay attention, unfortunately or fortunately, because your next homework will ask you to implement this boot sequence, which conceptually is very similar to what I will be showing today in the slides, conceptually similar to what x86 is doing. So essentially, you will write this sequence. You will boot into main and print hello world on the screen next time, so in the next homework. Okay, so today, yeah, booting into the kernel. Okay, cool. So I don't know how many people know about how the hardware boots. In practice, PC hardware, which we're running, I mean, today, because many people run Mac as well, which is not a PC architecture, but conceptually it's similar. So the whole boot sequence is a little complicated. And there is this document, again, written by a professor from MIT. It's called Intel SGX Explained, and it has a good start on that. So if you want to know the details, like you can read section 2.13. It's a lengthy section, so I will kind of like just give an overview of this. It will be helpful for you. So like in many cases, it doesn't matter. It matters if you become a security researcher. And towards the end of this lecture, you will understand that, like if you really care about security of your machines, you really have to care about security of your boot sequence. And there are people hired for money to make sure that, financial companies have their data centers secure. They're fun people, those guys. They're very, very knowledgeable as well. Okay, but at a high level, like again, machine goes through the stages of initialization, right? And like we'll see a couple of those pieces of software, and I don't know if you ever heard those words, but probably you've heard BIOS, right? And all of these things are actually running on your machine nonstop, right? So the high level idea here is that really you don't even own your machine, to be honest. Okay, so, and that's my slide. So essentially, the operating system is not the only piece of software running on the machine, right? And again, like most people know that, okay, there's virtualization in a data center. Maybe you even run hypervisors locally sometimes to run Linux on Mac or something like that. But really, there are at least two layers of software which constantly running underneath. One of them is called a system management mode. And just to give you a hint, like you probably have seen that you can recover your machine. So if it's some catastrophic crash on many laptops like HP, Lenovo, you can press a sequence of keys on the keyboard during the boot, and it boots you into some environment, and you say, "Wow, restore operating system," right? So it's done from the system management mode, and I will explain later how it runs. But we call it ring -2, sorry. Because remember, operating system, I was saying, runs in the most privileged ring, which is ring 0. Say again? 0. User runs in ring 3. Hypervisor runs in ring -1. And the system management mode is underneath the hypervisor, and we call it ring -2. It's minus means, minus is a joke, right? So it shouldn't exist, but it does exist in practice. It means that it's even more privileged than the hypervisor. I will explain in a second, but it can take control over any machine almost any time. Yeah.
How many of these levels?
Good question. So this ring -2 and this ring -3 are really gifts from Intel. So they shouldn't exist, but Intel said they will exist, and I will explain why. Why? Because you don't really control them. And as I said, it's very hard to secure your machine, and if you don't control a couple of layers of software which runs underneath, right? So because someone wrote them, someone can kick in at almost any time. You probably have heard of those solutions. Like when I was a student, I was buying laptops on eBay. You can buy them for cheap, because the big company just discards old laptops. They just take out the hard drive, but they say, look, but by the way, on this laptop, there was this system management mode-based solution installed, which was monitoring their employees, right? And supposedly it's disabled at this point, right? So like I had a cheap Lenovo laptops. So that's one way to essentially screenshot what you're doing at any moment of time, or inject something into your operating system to say, look, are you really like working, or are you just goofing around? So that's done through this layer. And this Intel management mode is yet another piece of software which is also running on a machine non-stop. And I'll explain in a second where it's running. And it's ring -3. And if you, again, at some point, like officially, we say, look, those should be the rings advertised by Intel. Ring 0, ring like 1 and 2 and 3, right? Then we have virtualization supports. Okay, we have ring -1. And those two other rings, and maybe if you, again, if you're a security researcher, you might count a couple more if you like. They're like, that's essentially a terminology from a security research. They said, okay, look, really, it runs underneath. Let's call it ring -2. Let's be honest about it. But really, you might discover yet another ring soon because Intel forgot to tell you about something, right? And there are pieces of software which are running there. So you can argue that maybe there is ring -4 or something like that as well, like microcode and stuff like that. Okay, so let me show you like where those things are running. So this is like a motherboard for a standard PC machine from a couple of years ago. And again, I keep drawing this diagrams of how what's inside this, what's inside on the motherboard. And roughly speaking, when you buy a PC, you buy a machine with one CPU, right? So you buy one physical CPU. It's connected to a set of DRAM banks, but like they will be like sticking on your motherboard, right? Maybe you bought 4 or something, right? But it's like connected to like a single memory controller, right? If you, and in my slides, I usually draw it like that. I say like one CPU, one memory bus connecting a set of DRAM chips, and then there is a like PCI bus, which is a main bus which connects you to peripheral devices like SSDs or NVMe drives, network interfaces, then additional microcontrollers which implement logic of connecting to older hard drives, like it's called SATA, and implement USB interface, right? And if you're really in a data center, so this is like a picture from a data center, which is called Emulab, which is sitting on like in MEB on the 3rd floor. You can go peek through the window. Their most powerful machines are those, again, like as of a couple of years ago, maybe they actually acquired better ones. So it's one of the most powerful like PCs you can buy. So it's a Dell R830. So it has 4 sockets, meaning that if I draw this diagram, there will be 4 different physical CPUs, right? Like each of them will have its own memory controller and memory bus, and each of them will have their own PCI bus, so you can have multiple network interfaces and stuff. And all of it will be connected through those cross-socket links. And a couple of years ago, it was called QPI. Now it's called UPI. QPI was standing for Quick Path Interconnect. UPI stands for Universal something, I guess. Doesn't matter. But the point is that, again, going back to this diagram, so in reality, you can have like a bunch of sockets connected with some kind of cross-socket link, right? And that sits on the motherboard, right? So these things you will buy individually, right? And this other part here, it actually runs on the motherboard, right? And there is something what is called this PCH, Platform Controller Hub. So essentially, it's a collection of microcontrollers which sit somewhere on a motherboard. So if your CPU will be somewhere here, right, your memory will be sitting in those DIMM slots. I would guess that on this motherboard, under this like heatsink, passive heatsink, there will be this PCH thing, right? And again, if you ask yourself, what's inside there? Question. Heatsink, just Well, their heatsinks are passive cooling elements, right? So that's what I would meant by this. I'm not even entirely sure that this is a heatsink or just an element which is like designed for protection, but most likely it looks like a heatsink, right? Like typically on top of a CPU, you will put some active fan, which actually spins, right, and sucks out the heat, right? But like good laptops these days have like passive heating as well. Like your phone has obviously passive heating elements, just so it avoids the noise and it's less power hungry. So, and this is where this Intel management engine, which I was saying is ring -3, is running. So really on this on the motherboard, so this is like if we split it, right? So this everything, this part of is the motherboard, right? It sits there and it runs. And if I tell you, okay, what's inside? So inside is actually a full-featured Intel x86 CPU. So each motherboard today comes with this Intel CPU on the board, and it cannot even boot. So like without it, right? So there's a couple of peculiar things about this CPU. So it has its own DRAM, so 1.7 megabytes, not a lot, right? So if you want to write operating systems for this Intel management engine, you have to be careful, not much memory, right? The funny part that is it has actually access to the main DRAM, right? Means that it can read memory of your machine at any point of time at will, right? We are a mechanism which is called direct memory access, DMA. As I said, you cannot even boot without touching the Intel management engine. So just PC machines don't boot, right? So it controls the boot chain. And the funny part that it actually has access to the network interface, again, which is funny, right? So, which means that, and it has a power line. So you say you close your laptop or even like you shut down your PC, but as long as it's connected to the power line, like to the actual outlet, Intel management engine has power and can run. Yeah.
So is this guy on the BIOS chip? Oh.
Hold on. BIOS is a piece of software. I will explain in a second when BIOS runs. So BIOS is software, and there will be a piece of during the boot chain, the pieces of BIOS will get initialized into a special hardware compartment, which will be protected from the rest of the operating system and the hypervisor, and it's called system management mode. That's where I said, software companies are using to monitor their employees, right? This guy is almost I think it's entirely controlled by Intel. It sits on a separate x86 chip, which sits on the motherboard. And before anything even boots, it has control. And when you shut down your laptop, it still has power, which is funny, and has access to the network interface.
So is
No, no, it's not BIOS. It's a different software stack. It's specifically designed, I will explain it in a second, but it's designed to provide this use case supposedly, or like what is supposedly? That's one of the use cases. Imagine you have a laptop, right? As I said, like this is like S5 is a power state. So it means that like machine doesn't have power on a main DRAM. So it's kind of in a deep suspense state, but Intel management engine still runs, has power, has its own memory, has its own operating system, which runs on it. And as long as, your laptop has, you can buy laptops which have cell modems, right? ME management engine can access this modem. And so essentially you can disable your laptop if it gets stolen. Essentially like remotely send a signal over that cell modem saying, okay, the laptop will no longer boot ever, right? So obviously, this is nice. So Intel gave you this gift of remote management. So essentially providing you a way to manage your machine remotely, right? But obviously on the other hand, it's a huge opportunity for the attack, because if you say, okay, so well, first of all machines contain ME, it doesn't even boot. but like good luck to you designing a piece of software which is bulletproof, which is not prone to attacks, right? So, okay, that was a couple of questions. So, and I moved forward. And again, so if I ask you a question, so for many years, first of all, this technology was like somewhat in a shade, right? So I mean, like people knew about it, but no one really knew about what's really running there. And then maybe around 5 years ago, so security researchers got to this point when they said, okay, like we will typically all the software stack is heavily encrypted. So there is still no access to the real code which runs on the Intel management engine, right? But what got leaked is the strings. Essentially, the strings table was not encrypted, and so the moment it became known, so people started searching for, like, started looking at those string tables, right? And these are the messages, these are the strings which you can find in this binary which runs there. And if you simply do a Google search, like verbatim for this string, it lands you surprisingly on a piece of code which is developed by a guy whose name is Andy Tenbaum. And I don't know if you ever seen his books, but when I was a student, he wrote a couple of very good books about operating systems, how networks work. People used to teach operating system classes based on his books. And he also built this, or him and his team built this operating system, which is called Minix 3. It started as a teaching operating system, Minix 1, similar to XV6, just to teach students how operating system works, how operating systems work. And then later on, he turned it into a research project, which is like a full-featured microkernel. And essentially, if you look at this file, you see that, okay, look, this is the string, fs bogus child for forking. So you clearly know, like, you don't clearly know what's running, but most likely, at least something what runs on the ME either completely uses Minix or uses parts of Minix, because why would you like take parts of the like file system implementation from Minix and just like randomly ended up with the same strings, right? So essentially, there is a very good chance that every Intel machine runs this Minix microkernel, which was a little bit like, patched by Intel to make sure that it runs on ME. I mean, maybe it was heavily changed. We don't know. But again, if you carefully look here, so it's our good old C code, right? So your density, like first 10,000 lines of code, you will find a couple of bugs, right? And so not surprising, bugs were found in this Intel management mode, right? So you can go online and Intel releases those patches saying, okay, look, yeah, actually Intel management mode was running a web server, of course, buggy, and like you can break in and like control your machine remotely, right? So there were those exploits, which is a lot of fun, right? Well, that's an interesting design decision to get a piece of software running on your machine which you don't control, don't know what it is, right? And but it controls everything in the world essentially. Right. So NVD, it has a similar technology. Let's put it this way. It's not my domain, right? So I'm not like I do security research, but slightly different. So I'm not like digging binary string to find exploits. I build more secure operating systems. So my goal is to come up with a tool chain which allows you to build an operating system which can run inside ME. It has 7 guarantees about correctness. So it's much harder to break in, right? But maybe I won't be next. We will be running inside ME. Unlikely, right? But that's kind of cool. Yeah.
A way to remote control
No, it just this is like if you very carefully look here, so it's they just search, like we can search right now, and it is part of the file system. So it's part of the virtual file system inside the Minix microkernel, right? And so it just implements like parts of the file system, but those strings are found inside Intel management engine, which well, but yeah. And it's a layer which abstracts certain parts of the file system, meaning between the operating system kernel and multiple different file systems, which the kernel can implement, like, NTFS, whatever else.
So here is an example, say, to remote access the system.
No. Like to really get control, you have to find an exploit. If you want a remote access, you have to find an exploit in the network-facing components, like a web server, and then break into the kernel to get root privileges. Or if you're lucky, you can find exploits in the network stack itself, in the network device drivers, like send a magic packet and maybe you forgot to allocate memory or something like that properly.
Sorry, I didn't get this example. I didn't get the point. So
No, you're welcome to talk to me. Let's just move on, because the point is that this example explains how people, this slide is done by the company, which is called Positive Technologies. They were essentially trying to understand what is running inside Intel Management Engine. And the only clues they had are those strings. So they did analysis, because the code itself is encrypted. I don't think it was publicly, at least as of a couple of years ago, it was at that point, it wasn't decrypted or publicly known, right? So, and they said, okay, look, we only see the strings. We analyze what the strings might be. It looks like that Intel Management Engine is relying on the operating system, which uses parts of the Minix 3. And Minix 3 is just a regular, like, it's a microkernel, but it's of a quality of x86, let's put it this way. Maybe better, but close. And this thing controls your machines, right? So if you run a big bank, then you have to be careful, right? Okay, cool. So what is the role of this ME? As I was saying, it controls the boot chain. So in fact, it gets the power first, right? So it sits here on the platform, on the PCH, right? And it's essentially gets the power. And what it does, it just starts reading from the read-only memory, this flash. It essentially starts reading the BIOS. So the code of the BIOS, right? Okay, cool. And first, it starts reading its own code to boot. It boots, and that starts reading the BIOS. I will skip a bunch of details. So it's kind of a high-level overview of how the boot goes, right? But at some point, this, like, multiple CPUs, even if you have one CPU and multiple cores, one CPU is assigned as a main bootstrap processor, BSP, and other CPUs become application processors, or APs, right? And they are just simply waiting for the one processor to boot. So, like, technically speaking, and we'll see it later in x86, only one CPU is booting. Everything else is just sitting idle waiting, right? So then, okay, so I said that BIOS is a piece of software, right? So essentially, this BSP starts by executing instructions from the BIOS, right? So which are accessible. And an interesting detail here is that DRAM is still disabled. In fact, to enable the DRAM, you have to load a couple of software modules, which Intel gives you, and they kind of initialize the DRAM. And at some point, it becomes looks like a real DRAM. So here's the question, like, there is no memory. The CPU is running, fetch, decode, execute loop is running, but the DRAM is not there. So you cannot really push anything anywhere, right? So what can you do? If I ask you a question, can you write me an assembly sequence which never touches the memory? Yeah. It has access to this flash read-only memory where the BIOS is sitting, right? It has access through something what is called an SPI bus, which connects, essentially this CPU has a connection to this PCH, and then like this, right? So I don't know the details of those buses. Again, like, I never played with them, never really like look into the details. You're welcome to look. It will consume your life, but it's a lot of fun. And maybe you'll become So you will like people who are working at this level and dedicate their lives into like kind of reverse engineering what Intel is doing and trying to secure the system, trying to arrive to a better architecture because they essentially expose the attacks. So there are multiple attacks which are possible, which, you know, Intel engineers, they're like us, you know, they graduated from Utah or somewhere, went to Intel, and like you work for them. Like imagine like you have limited knowledge of it. So, and when the community kicks in, there are multiple attacks which are immediately like surfaced. But at a high level, yes, it can. The fetch, decode, execute loop somehow manages to like read the bias. You had a question.
Well, just from, I think this might be how it works, but can you just use like the cache of the CPU to hold it?
Next step, caches are also disabled, but they enable the caches first, use them as temporary memory, and then because you can only do minimal, like limited stuff when you don't have a single, like, you know, you cannot save anything to memory. Your computation is severely limited, right? But yeah, so the next step is actually enable caches and then enable memory. And enabling memory is like a black box. I guess it's so complicated that only like DRAM manufacturers know how to like properly initialize them. Because I think like, I don't even know whether it's, I think it's publicly available, but the code is like some magical instruction writing something on some magical buses, right? And that's where we are. So we don't have a good spec of how it can be done. So there was another question. Right. Okay. So yeah, you can like really write a custom written assembly code, but as I was mentioning before, people came up with this read-only memory C compiler, and it's used as part of the Core Boot project. And I think Core Boot is was used on Chrome laptops to implement their boot toolchain, right? That's a lot of fun. Like, so essentially it just generates the C code that doesn't use stack or anything, or doesn't save anything to memory, right? And as you were saying, so the next step is to enable caches and use them as temporary memory.
Was the code that the management engine reads from the BIOS chip separate from the code that's executed by the bootstrap processor?
Separate, right? Because Intel protects heavily protects the code of the memory engine. So the code, they sit on the same read-only flash drive, right? And Intel management engine first, or this PCH essentially, when it boots, again, I don't know the details of how PCH boots in details, but at a high level, it reads the code of this Minix operating system. Let's assume it's running there. Puts it in this x86 chip, which sits on the motherboard, decrypts it, and then it starts running. And then Intel management engine kicks in the CPUs and they start booting. And again, the main bootstrap CPU reads again from the same BIOS, from the same flash chip, but slightly different memory region, reads the BIOS software. So the BIOS software is different. And I mean, you say you're in control, so you can reflash the BIOS, you can remove it from the machine, but it just unfortunately doesn't boot after that. So today, the only way to disable Intel management engine is to let it boot, and then you can attack it and kind of almost disable it. So that's the way as of a couple of years ago. But then BIOS is critical. Again, if Intel management engine is mostly needed to control the machine remotely, BIOS is really needed to initialize everything on the machine. So BIOS is a collection of the software blobs shipped by different manufacturers, which say, okay, you need to run it to initialize a network card or a memory or everything. Right. But yeah, go ahead. Question.
You said that the BSP starts with the RAM disabled, and you also talk about the RAM, ROM, right?
Say again. BIOS, yeah. So BSP starts with DRAM disabled.
Okay. So BSP starts with DRAM disabled, so it does not have any memory.
Yeah.
So you only use the register.
Yeah. Okay. And again, maybe it's two level. For this class, maybe it's too low level. And my information here comes from this document written by MIT professors. But it's just fun to see that how complex this thing became. And again, in our class, we will just like stick to the high level line, which we'll like get to in a second, right? But essentially, okay, so the goal here, initialize the DRAM, then read the BIOS firmware, like kind of like linking and loading, read it from this flash drive into the DRAM, starts executing it. And essentially, as I was saying, BIOS is responsible for initializing all the parts on the motherboard. So for example, some of your network cards will require a piece of software to boot. Like the network card itself runs a tiny, I mean, you can call it an operating system, but it runs a tiny blob of software, which people call firmware, which has to be loaded there because, and it varies, but essentially, yeah, so BIOS helps to execute those boot protocols, right? So those are called option ROMs. So which are like which initialize the network cards and whatnot, right? But there is a lot of software running, right? Because imagine you have an SSD, right? So it does a lot of like translation between logical block addresses and real addresses on the flash arrays, right? So okay, cool. So as I was saying, there is another piece of software. This is ring -2, right? There is a mechanism on Intel, and AMD as well, which allows you to designate a region of physical memory and protect it from making it essentially invisible to the rest of the system, right? And this is where BIOS, which one would imagine BIOS only runs during the boot, but no, on Intel, they initialize this region of memory, load some software in that region of memory, and there are special interrupts which sometimes return control to this software, right? Like I'm running Mac laptop, so architecture is slightly different. But up until like this year, I was running Intel, right? And so essentially, once in a while, this thing kicks in, and whatever, I don't know what's running there. Lenovo, I was using Lenovo laptops, put some piece of software. It can do anything to my machine, right? It periodically gets control, does anything, can access the whole physical memory, can write into memory, can inject a piece of software into my operating system, right? And it will be running underneath, right? Monitoring what I'm doing, right? And again, there is no good way to disable. So like today, it's possible only by attacking this boot chain. So essentially like finding a backdoor and say, look, like we will attack and disable it. So, but this is ring number -2. So if you're working for those software companies, which say, okay, we're gonna like periodically peek at your screen, this is how it's done. And this is essentially the environment in which you boot when you want to recover your machine. Okay, so, okay, we have a couple of pieces of software running. So that's mostly for just general information. And again, I refer you to this document, Intel SGX Explained, which studies the boot chain. But what we care about is kind of this punchline. So BIOS, and this is the protocol between the BIOS and the rest of the software, right? So BIOS ends by loading something what is called a bootloader. And this piece of software is actually ours. So we write it. So like in x86, and in a second, we'll take a look at the source code of the bootloader, right? And again, you've seen that BIOS can boot from different sources. You can boot from the network, you can boot from multiple drives, from USB sticks. If you think about it, it's kind of like a little tricky because to boot from the network, you really need to have a network stack, right? TCP running and stuff. So BIOS itself is almost like a tiny operating system which implements all this. Like it implements multiple file systems, which can access USB, optical disks, right? It implements network stack. So it's a big piece of software, right? So also easily attackable. But at a high level, in our simple scenario, and this is how like typically your machine boots by default. I mean, used to boot as of 5 years ago, because now we have EUFI, which is a different BIOS standard, which is a little bit more complicated. So not going to go into these details, but essentially what BIOS is doing is by default is it will read the first sector from the disk, and sector is only 512 bytes. And the convention is that it will load this first sector into memory at address 7C00, and it will just start executing instructions from there. So if you want your bootloader to get loaded by the BIOS, you just copy into the first sector of the disk, and this is how you get control of the boot chain after that. Okay, and this is exactly when we will be running cs6 under control of this QM or virtual machine monitor or emulator. It actually executes BIOS, so it's like it will execute the same boot protocol, and the way you get like a chance to run is to essentially compile something what will be loaded at this address 7C00. And this is where we start. So essentially, if you don't want to know anything about how the system boot, this slide is kind of enough for our class. You just say, look, something was running before me. I don't really care that something loads the first sector of the disk into memory location 7C00. And at that point, I'm running, right? Okay, and this is our kind of graphical representation. We have a CPU, it's all initialized. It still runs in real mode, which means it only has 16 bits. It has no segmentation, no paging, just physical addresses. And something or some piece of software which we can write is loaded into 7C00, and it's only 512 bytes. And now our instruction pointer exactly points to 7C00. That's the protocol between the BIOS and the rest of the system. At this point, BIOS should quit. Unfortunately, it still is running in this system management mode somewhere hidden somewhere here from us. We cannot even access this memory, but like whatever. Assuming it's not running, now we are running. Questions? Somewhere here. Maybe actually nothing to the left. It's available to you. There are some magical regions of memory below the first megabyte in which you write. And maybe remember I was saying it implements a frame buffer. So it shows up on the screen. Like if you print hello, you write somewhere here, right? We'll see in a second.
Thinking first, it's a fixed place, so there must be some security issue. The second point is this is kind of like risky because if this just partly broken, we could not boost the system.
Right. So I honestly didn't get your, like, you should clarify your security concern here, but really BIOS, which was running on this CPU before us, says, okay, I will exit the disk. By the way, it knows how to exit the disk and reads the sector 0 from the disk in this memory. And at this point, it says, okay, I'm done running. It's your turn. I will just set the instruction pointer to 7C00. You do whatever you want. If the boot block is corrupted, then yes, the system will not boot. And that's easy. So again, as a child or as a student, I broke my boot blocks multiple times. And you might break some in this class as well. But yeah, when you will be doing this hello world, essentially you will have to implement some code which correctly does this sequence. And I'm going to discuss what you should do in a second. Other questions?
So you were saying that BIOS is at the system.
Yeah.
So BIOS is kind of like -1.
No, BIOS supposedly only should initialize everything and never run after that. So technically speaking, the code of the BIOS will not be running, but BIOS will initialize this hidden compartment, which is called system management mode. And we call it ring -2. And it can load itself or parts of itself. And then periodically, the CPU will receive like magic interrupts, which will redirect control here, right? And it runs and does something. And if your software vendor who builds your system provides you a way to inject your own software here, you can run in this compartment, which is a little scary. Okay, good for now? Okay, so sure. So now we are in control. All this Intel, everyone else, motherboard manufacturers, they are responsible for the BIOS. We as system designers responsible for the boot block. So, okay, if I ask you a question, what is that we need to do? What's next? We're in control now. We're running the machine. So who can outline me a boot sequence? Say again.
Go into the kernel.
Well, okay, at the very end, I will say, we want to get to the main function of the kernel, right? I agree with that. What's before that? We have to do what? What do you mean program itself? Well, imagine it's already written and we saved it on disk, for example. So it sits on a disk. Remember, we only have 512 bytes, right? That's what's running right now. Like not much can be done in 512 bytes, but something can be done. Yeah. Exactly. So we need to switch to 32-bit mode, right? Which means that we need to enable segmentation. We can stick with segmentation, but it kind of makes sense to enable paging as well, right? So we can like access all 4 GB of memory, right? All the segmentation can do that as well. We also need to load this kernel from disk into memory, right? Don't be surprised, the kernel will be an ELF file, right? That's why we were spending so much time thinking about what's inside the ELF, right? And we will load this ELF in memory, right? And because originally we're restricted to only 512 bytes, right? But really we want to load the kernel in memory. If we want to run C, we want to set up some kind of a stack, right? Because like we cannot call functions or they just don't have binary compatibility with, like don't have the runtime for running C, right? And at this point, maybe we're done. At this point, if we have a stack, set up the paging, set up everything, we can just jump to the entry point of the kernel and start running the kernel, right? Okay, let's take a look at how we're gonna do it, right? And this is my slide, which does the overview, but you more or less you kind of guess most of it. Okay, so this is the first time, I think, or nearly the first time when I really start talking about the source code of the kernel, right? So here at the bottom, I show you the file. So this is an assembly source code from the file, which is called bootasm.s, which I also like provide a tiny description here at the bottom saying that it actually implements the bootloader. So it's not yet the kernel, it's just the bootloader. And this is where the BIOS itself loaded us. So it has this like, we're gonna link it in such a manner that the start label will be loaded at 7C00, right? And this is the very first instruction which the bootloader executes after the BIOS. And what we're doing here is we're immediately disabling the interrupts because maybe BIOS left them running. So because it was communicating with the disk and stuff like that, it loaded us after all, right? So what we do is we invoke this disable interrupts instruction first. And then what we do is that say, look, maybe BIOS was doing some kind of, maybe it had segmentation enabled. So just let's make sure that everything is 0. So essentially we use the XOR instruction and zero out the EAX register. And then we move EAX into all this data segment, extra segment, stack segment, stuff like that. So essentially just making sure that the environment is clean, right? At this point, you say like this is really your 7C00, you're running here. Those instructions are running right here. And if I ask you a question like, how can we make sure that the start label or the code which we're going to be running can run at this address 7C00? So what kind of trick we have to do? That's related to our wonderful linking and loading and relocation sequence. That's why we spent some time on it, right? And I like, even in the homework, like maybe I deleted in the most recent version, attempt to relocate or link the file to run at a specific address, but you can actually tell the linker. And this is what x86 is doing. So essentially it has, when you build this boot block with the main file, with the make file, sorry. So it's built out of two source files. One is assembly file, boot as.s. This is the one we were looking at. And one is a C file, boot main.c. It's easier to program in C than in assembly. So we're gonna do as much work as possible in C, just using assembly just for tiny initialization sequences. And here I specifically, not me, but whoever wrote x86 says, okay, make sure that the entry point is a start label in this file, and the text section is compiled and linked to run at 7C00, right? That's convenient. So we know that the C code will run. It will generate out of this C file. It will produce some kind of a data section, right? So nothing will relocate us. BIOS will not relocate us. So we have to make sure that this code is ready to run there, right? Okay, cool. So this is, we understand how it can be done. Again, kind of similar to how you predicted that our goal is to start switching to protected mode or 32-bit mode of execution. So that's why we spent some time talking about global descriptor table, and the instruction on Intel which does it is this load global descriptor table register. So essentially, remember that the CPU knows the position and physical memory of the global descriptor table. And this instruction actually does it, right? So like essentially in our C or assembly file, we say, look, we're gonna allocate some memory in a data section. So it's part of this 512 bytes, and it will contain entries for GDT, right? So specifically, we only need 3 entries. There is a convention that entry 0 never used, so it's like always null. And we only need one code section and one data section. And we don't care about protection or anything, so we just make them like from 0 to the max 4 gigabyte address, right? So very simple global descriptor table. But again, you need the global descriptor table to make sure that it can switch into 32-bit mode of execution. And just again, just to remind you this wonderful translation scheme, right? So you have segmentation first. It uses logical address, which consists of 2 parts, like a register which selects the entry in the GDT and the actual offset in the instruction, right? And then whatever you get out of it is called the linear address. And typically in most classes, we call it virtual, because like this translation translates like has no effect because the base is always 0, right? And then we translate with a page table, we translate from virtual to physical, right? Okay, cool. So we know how to do it. So how do we define a global descriptor table? We use a bit of assembly macros here. So I define just a label here saying, okay, this is where in the data section GDT will be. And those macros just expand to define actual bytes, and just they help me to initialize. This is the code segment. So I say it will be executable and read-only will start at address 0 and will go up until the max address. And this data segment will have a slightly different format. It says it will be writable, but not executable. Again, we'll start from 0, go to max address, right? And this instruction, which loads the global descriptor table register, actually, it requires the following argument. So it requires the size in a first, as a first argument, it requires the size of the GDT. That's why I compute here, like the distance between this label and this label minus 1 byte, and the address of the GDT. So essentially this address, right? Again, a little bit of a low-level details, and we will go over it in the homework because you will have to define your own global descriptor table and like initialize it and stuff. And there will be like instructions for how to do that, but just to explain. Okay, cool. So any questions about it?
Why we not read it exactly right?
No, it's a code segment. No. Write means read and write. There is no. Yeah, so CPU just distinguished between read-only and writable. So we can write. Any other questions? Okay, cool. So we got this global GDT desk label, and this is what we're really loading in the global descriptor table. And after that, so this is actual, it's called the long jump. So these actual sequence essentially tells you, please jump to the label, start of the 32-bit code. This is where the next instruction will be executed as 32-bit instruction. And please use the code segment as a code segment register, right? And we shifted by 3, and this is because the actual format of this is that the actual index, so our goal is to put 1 here, right? Because the code segment was entry number 1 in our GDT, and these lowest 3 bits are just flags, right? So here we request the privilege level, we want it to be 0, and this is the switch which says, okay, use global or local descriptor table, and I never explained local, so we use global. So this one is also 0. So we shifted by 3, right? Okay, got it. So now our, again, system looks like this. So our code segment here has entry 8, because if you shift to 1 by 3, so binary 1 0 0 0 equals to 8, right? And the code segment points to this entry, and the instruction pointer is the 7C1D, because we executed a couple of instructions here, right? So now we have essentially protected mode. So we run and use GDT. We run in 32-bit mode, right? And all addresses go through the GDT, right? But our GDT is so simple that it just simply says, okay, nothing gets, the base is 0, the limit is max address, right? But fine, we're ready to do that, right? And when we landed on this label, we say, look, by the way, we need to access data. So essentially, we load the entry which points to the data entry in the GDT in the AX register, and just essentially load AX into DS, ES, SS, all data segments essentially, right? And those two we're not going to use for now because we're not going to use FS and GS, so we just put zeros in those just in case to essentially like catch an error. If something goes wrong and we try to use it, we'll land on the entry 0, we'll get an exception here, right? Okay, so the system looks like this, right? We might have maybe only 512 megabytes of physical memory. If we try to access our segment somewhere here, that's unfortunate. We're going to crash because the machine says, okay, you don't even have memory there, just because we were lazy in our segments. We didn't even detect the max available physical memory. It's possible you have to query the BIOS and ask the BIOS, okay, how much memory do I really have? For simplicity reasons, x86 doesn't do that and just simply assumes that there is some max address, right? But it's not super hard to detect. But that's what's running, right? So you say, look, I have a GDT, my code is running here, my instruction pointer points here, right? Our next step is we're going to set up the stack. Why do we need the stack? Again, I'll ask you a question. Right. So no, like real reason we want to switch to C, right? So because everything what was shown before, you cannot really do in C because C doesn't have primitives. I mean, it has support for inline assembly, so you can probably kind of fool yourself and say I can do that in C, but really C is the language which is not at the level of details, right? So you cannot really like load anything in GDT and C, right? So you need assembly. But the moment you can jump into C, jump into C. But in order to invoke the call instruction, you need stack. So you say, look, let's load this value in the 32-bit ESP register, right? And if I ask you a question, right? Look, do you remember where the start label is? Where was it? Like, right. So like it just like, let's just spend a little bit. So this is where it is, right? This is the start. It's the very first byte of this boot block at 7C00, right? So why is it I'm setting the ESP register to point here? Where will be my stack now? Not really overwrite. My stack will start growing this way, right?
Oh,
And why is it I'm doing that?
because if you're writing this,
No. I'm just choosing memory for the stack. Correct. So I can pick any address. Remember, I was telling you that stack can be anywhere. But if I accidentally put it here, there is no even physical memory here, I might crash. Here, I know there are some addresses of the BIOS, so I don't want to write into them because machine might crash as well. But I kind of know that this area is empty, and I just put it to say, look, let's use it for the stack right now as a temporary stack. But it's your power. If you understand what stack is, you know where to put it, right? Okay, so cool, we did it. So we said, okay, let's put the start label and it will be growing down from there, right? And then we call into the boot main function. And the machine will look like this. So we have this blue stack, which grows down from the 7C00. And at this point, we are ready to call the C function. And this is the very first C function of the bootloader, which we're running. So our goal in this function is really to read the kernel from disk, right? Because that's what we want. And that's what we're doing here. So we say, look, this kind of familiar from the homework. So the kernel is an ELF, right? So and we will say, look, let's again pick a different address, which we also know is available. And this is where we believe will be our ELF header, right? And we just say, read the disk or one page of the disk for 4096 bytes into this memory location, right? And if I ask you like what we're gonna do next, it's kind of like, it's similar to the homework. So essentially you say, look, I will be looping through the entries of the program header and essentially just loading them in memory, right? And eventually what I will do, I will assign the entry point of the ELF file to my entry and I will call into it. And this is where I start executing the kernel, right? Why not? And so if you ask me a question, how do we read the disk? So again, it's a very simple protocol. The details are not as important, but you essentially just configure the hardware by using these in and out instructions. So some magical addresses in the in-out space define what has to happen. You configure your write. You then just wait for the disk to make sure that it's available. So at some point, you just keep polling in a loop until the disk says, yes, I'm ready, my command is executed, so you can move on forward, right? So you can look at the details of this protocol. So it's probably not very important for us right now, but at a high level, that's the very simple way to read the disk, right? Okay, so you read the kernel in memory, you getting ready to invoke the entry point essentially, right? So the entry point of the kernel will be again an assembly sequence, right? So why is that? It will become clear in a second, but really up until now, we haven't yet set up the page table. We only set up segmentation in a bootloader. So the kernel will be responsible for setting up the page table, right? And again, you can do it differently. You can say, look, why not to set up the page table in a bootloader? Well, it's totally possible. It's just the design choice here. But at this point, cool. So again, I'm showing you here the file on the screen. So it's entry.s. It's part of the kernel. So because the bootloader loaded the kernel in memory and executed this two lines, which essentially jumps to the entry point of the ELF file, which we loaded in memory, right? And essentially, this is the entry point of the kernel. And this is the very first instruction of the kernel which will be executing, right? Is that clear? And the world looks like that. So remember, we set up the scratch space where we read the ELF header. And this is where we actually loaded the kernel into, right? This is our stack. This is our bootloader. This is our GDT. And I say start here, but really I should probably say entry, because this is how the kernel calls it. Okay, cool. No, actually, I'm right. So the global value entry actually matches the start, right? So it's a start label. Okay, cool. So what's next? What do you think we're gonna do? I said we're gonna set up a page table. We can go ahead and set up a full-featured page table, which we again discussed last time. But kernel makes a slight simplification. It says, okay, at this point in time, I don't really need a a fine-grained page table. And since there are two page table sizes which x86 supports, I will go with 4 megabyte pages because I will really only need 2 pages of 4 megabyte each mapped in memory, right? Just to like a quick recap. So this 4 megabyte pages is just one level of translation, right? The top 10 bits of the address define one of the 1024 entries in the page table directory, right? And those entries will contain the physical page number of a page, right? Agree? And this is your like diagram from the Intel manual, right? Okay, cool. So, and well, we say, look, like on this slide, what we executed here, we say, look, first of all, turn on the page table extension. So what you do is that you read the control register 4 on Intel into a register EAX, then enable one single bit, which says page table extension. So essentially it says like use 4 megabyte pages or enable them essentially and write it back in a control register 3, right? The reason is that you cannot really do an OR operation on the control register. So you have to only, like it only supports read and write. It's like one of the control registers on Intel, which essentially contain the flags which control the behavior of the CPU. And this specific bit controls that the 4 megabyte pages are enabled, right? And what we're doing here is that, remember, I was telling you like last week that control register 3 contains the physical address of the page table directory. And that's what we're doing here. We say, look, we take this label, which actually we'll take a look in a second what it does. It's array essentially of 1024 entries, which is entry page directory. Entry stands for the page table, which is only used during the system boot on entry. We load it in the register EAX, and then we load register EAX in the control register 3, right? At this point, the hardware is ready to use paging, but yet it's not on yet, right? So let's take a look at what is it we're doing here. So our end goal after we boot is to have the following address space for each process, right? The process text starts roughly linked at 0. Then we'll have process data. Some heap can be growing this way. Some stack can be growing in the opposite direction. And what's important here is that the second part of the address space belongs to the kernel. So the kernel itself has to be linked and loaded essentially to run at the second gigabyte, right? Why is that? It's just a design choice. You can say, look, what about if we flip this to, will it be bad? Well, not, it will be okay. It's just that it's a different address space layout. For historical reasons, I guess, people decided that this is how they wanted supported. Like in the operating systems in which I build today, we say, wow, forget about it. The kernel runs here, the user runs on top of it. Doesn't matter. So it's just a design choice. But if we want to do this address space in which the user runs at the lowest addresses, we have a little bit of a problem here because remember, we loaded the kernel here, right? So if we do one-to-one mapping, essentially saying, leaving the kernel in the virtual address space, leaving it at the address 100000, right? Then the user cannot be located here, right? So what we need to do is we need to really remap the kernel to be at the second gigabyte, somewhere here, right? And that's what our page table is designed to do. It will only have 2 entries. Entry 0, which maps the first 4 megabytes, or specifically from 0 to 4 megabytes to 0 to 4 megabytes virtual. So this is physical in my slide. And the second entry, 512, which essentially, again, maps the first 4 megabytes of physical to the addresses which start from 2 gigabytes to 2 gigabytes plus 4 megabytes, right? Yeah. So let me explain in a second why we're doing it. So it will become clear, don't worry. But what we're doing here is just we say, look, we want to define a page table in C, right? because we define the global descriptor table in assembly, but we don't really need assembly. So what we're doing here is that we just simply use an array of number of page directory entries, right? And not surprising, this number will be 1024, right? And we have this attribute to say that actually this array will be aligned at a page boundary, because this is how the hardware wants to see a page table. So essentially the C can tell you in the data section, this will start at some address, which is multiple of 496, but by some n bytes, right? And so we only care about two entries, entry 0 and entry 512, right? Okay, so let's take a look at what these are. Again, NP entries is 1024, not surprising, because we want a page table directory. Why do we care about entry 0 and entry 512? Who can tell me? What is so magical about those entries? And nothing else.
The first page of the kernel and the first page of the user space.
Correct. So in virtual address space, like if these are your virtual addresses, right? If you want to address a page, which is the very first page virtual page number 0, right? Obviously, like it's top 10 bits of the address. Remember, that's how the virtual to physical translation works. You will land on the entry 0, right? Because that's how the hardware says, okay, I will take the first 10 bits of the address, and it will be zeros, right? And this is the entry, and this is the page table, page directory entry, which defines how the entry is translated. And the second entry 512 is the very first entry at 2 gigabytes, exactly at the half of the address space, right? And this is where we want our kernel to be mapped, right? So we want our current mapping, meaning that the kernel is currently running here, and we want it to be mapped at the second gigabyte, right? And so is that clear? So it's a little unusual first when you look at the source code for the first time. So do we understand that here I just say initialize entry 0, initialize entry 512, and this is the actual value which will be stored in the array.
The question is why we don't put the so-called entry 512 to entry 1, right? It's normal to say, oh, entry 0 is start from the user space, and entry 1 start from the kernel space. That makes sense, right?
No, let me explain you what we want. Let's go here, for example. Our virtual address space in the end will have only two mappings, right? This is the very first, 4 megabytes from 0 to 4 megabyte address, right? So this is my address 4 megabyte. And this is the address 2 gigabytes to 2 gigabytes plus 4 megabytes. This is where we want the kernel address space, or the kernel part of the address space, to be located, right? So all of these addresses will be accessible or available to the user process. So your heap can grow up to 2nd gigabyte. And the kernel will be sitting on the second upper half of the address space. Again, so as I say, it's mostly a design choice, right? So you can, on Linux, you can split it into like 3 gigabytes and 1 gigabyte. So 3 for the user, 1 gigabyte for the kernel, right? But what you care about right now is just, you need to make sure that, if you want to enable paging, right? You need to make sure that you can run the kernel. And the kernel is currently sitting in the lowest, we loaded it here, which is like roughly first megabyte, right? And we want it to remap to be available at virtual addresses, which are about the 2nd gigabyte, right? And you say, look, in my page table, I only care about these two entries, the one which maps the first 4 megabytes, and the one which maps the addresses from 2 gigabyte to 2 gigabyte plus 4 megabyte, right? So if I put it in the first entry, then I would say my second page will be sitting right above from 4 megabytes to 8 megabytes, right? So these addresses will be available, but you don't really need them. Yeah. Okay, let's go back to here. So any other questions? So it's a little unusual. It's very unusual to see the very first page table defined in C to the point that I have to probably explain. I will explain in a second what these values are.
I want to be really selfish and say that I'm definitely going to rewatch this lecture over again because I've been having my team following along since we even talk about actually switching to space. But I guess something to start from is, can you explain again why the stack pointer is that so low? Again, is that ever changed?
It will change.
Okay.
It's just a temporary stack which shows.
Just a temporary stack.
No, don't worry, go for it. So I understand that it's a little unusual.
It's very dense.
Right. And there is a couple of there's a couple of things for how to approaches for how to understand it. So first of all, I will assign you homework and you will do almost the same thing yourself. It will take you a little bit of time, but over the spring break, and you will be able to boot. And I understand that it's impossible or nearly impossible to understand it from the first time. So it's not only that you will have to rewatch this lecture. At some point, you will have to work it backwards, and you say, "Look, I really wanted this, and this is how we got here." I'm trying to explain the bits, but it's very hard to make a connection. So I have two choices here. I can either skip, completely do not talk about it at all, and then just leave it to you. If you want to understand how the system boots, go for it. I feel it's a little unfair because then, there's a gap in knowledge and you say, look, suddenly we were not running and suddenly we're running in main. So it's nice to have this knowledge. It's hard to, I get it. So it's very hard to get this sequence from the first time. And up until now, I don't see a better way to explain it, fortunately. So it kind of goes sequentially. That's probably the plan, unfortunately. Yeah, this is a dense piece. So let me just erase everything here. But my goal here is to, when I read this code myself for the first time, not specifically this code, but a similar code of a different kernel, the very first kernel I read in my life, it was even hard to understand what these things mean, right? So how come this array turns into a page table? That's my goal today, to kind of explain what is going on here. So do we understand that this code in C initializes just two entries of this array? The entire array is 1024 entries. C will allocate space in the data section for 1024 entries.
Are those ORing 0? That's all flags that go along with that entries?
Correct. So who can guess what these are? What is it we're doing here? Or question? Correct, right? Because no, it can be any bits, but depending on what this, it can be a value OX1. So saying that the bit is present, maybe OX2 or binary 10, right? Saying that the bit is, the flag is, the page table entry is writable. Sorry, present is this one. So this is B1, this is writable, and S stands for super page, meaning that it's a 4 megabyte page. So do not go into the next level of translation. Question? Uh-huh. No, because kernel base is defined as 2 GB, and we are converting. Yeah, honestly, don't remember, but the final result of this is 512. So no, I get it. So kernel base is 2 GBs, but how do you get from 2 GBs to 512? So you shift so many bits to say this. Right, yeah, exactly. That's what you're doing. And okay, so who can tell me why those zeros? What are those zeros?
Is that physical memory at this point?
Correct. So this is a physical page number. So which means that our page table contains only two entries. Entry 0, which is virtual page number 0, which maps to physical page number 0. And entry 512, which is virtual page number 512, which maps to the same physical page number 0. So it's a page table with only two entries. The rest are 0. So which means that the bit present is not set. And which means if you accidentally try to access any address outside of these two small regions of 4 megabytes, you will immediately get a page fault, right? But that's how you initialize it. Or just tells you, okay, yeah, I will just essentially, or with a flag, right? Okay, so we're almost there. So at least do we understand how this array is constructed? At this point, yes. So by the way, early versions of x86, when the Intel hardware did not support 4 megabyte pages, really like we're constructing a 4 kilobyte pages. So essentially at top 1024 entries array of, and then those will, instead of like immediately pointing to 0, those would point to the leaf entries. And in order to cover 4 megabytes, you obviously need at least one leaf for each, right? Okay, cool. So this is nice. So we constructed this page table. If we load this page table, and I will stop in a second, just don't worry. Do you understand that our virtual address space contains, like the page table contains only two entries, 0 and 512. And it only maps these two ranges of addresses from 0 to 4 megabytes and from 2 gigabytes to 2 gigabytes plus 4 megabytes, right? And that's it. So the moment we enable this page tables, we can access addresses here, right? Anywhere here and anywhere here, right? So which is like, since our segmentation has a 0 base, you can access anything here. If you suddenly access somewhere here, that's a page fault, right? Well, it's temporary. We just want to transition. And I will stop here and I will come back and essentially resume from this slide on Thursday. So, okay, we'll finish boot on Thursday. We'll get to the main, I promise. Thank you.